Welcome back to the series on topology. In today's video, we'll be looking at quotient spaces. Because this topic is so important, I will split up the material into 3 separate videos. In this first video, we'll be defining what a quotient space is and seeing a bunch of examples. Then in the second and third videos, we'll be introducing the tools that allow us to efficiently work with quotient spaces. You can find a playlist containing those future videos along with all the other videos in the series by clicking on the info thing that should appear right now. Let's start by immediately looking at the definition. So for this, we suppose that X is some topological space, and now we consider any set Y, along with a surjective function that goes from this topological space X into Y. This setup then allows us to define a quotient topology on the set Y as follows. We let a subset U of Y be open if and only if the preimage of U under this surjective function Q is an open set in X. Okay, so in pictures, if we have our space X here, and we have any set Y along with a surjective function Q, then we can put this quotient topology on the set Y as follows. So if we have some subset U in Y, then we look at its preimage under the surjective function Q, which will be some subset of X. And we let U be open in this new topology we put on Y, if and only if this preimage Q inverse of U is open in the space X. One way to think about this is that we're pushing the topology that we have on X forward to the space Y along this surjective function Q. Now, based on this definition, it's immediate that Q is going to be a continuous map from the space X to the space Y with the quotient topology. This is simply because if we suppose that U is an open set in the quotient topology on Y, then by definition, this means that its preimage is going to be open in the space X, and that's just the definition of continuity. Moreover, the quotient topology is going to be the largest topology we can put on Y, such that this map Q is going to be continuous. Why is this? Well, suppose we had some larger topology on Y. So in this case, this topology would contain some subset S that is not contained in the quotient topology. However, because S is not contained in the quotient topology, this means that its preimage, so Q inverse of S, cannot be open in X. Otherwise, we would have included S in the quotient topology. Therefore, we have found a set S in this larger topology whose preimage under Q is not open in X, which means that Q is not a continuous map if we include this set S into the topology on Y. Therefore, any topology that we would put on the set Y that makes this function Q a continuous map from the space X to the new space Y with the topology will be included in the quotient topology. And this makes the quotient topology the largest topology we can put on Y such that this map Q is still a continuous function. Okay, so far so good. We've defined what the quotient topology is. If you're the observant type, you might challenge me and say that I've defined some open subsets and called it the quotient topology, but I haven't actually shown that these open sets form a topology. So let's think about why declaring open sets in this way makes the quotient topology an actual topology. For this, we need to remember the 3 conditions that need to be satisfied by a topology. The first condition is that the entire space and the empty set need to be open. Okay, so let's see if these sets are open or not in the quotient topology. For this, we apply the definition. We have that the preimage of the entire set Y, well, this is going to be X. This is just because, by definition, the preimage of the set Y is all the points in X that map to some point in Y, which is all the points in X because Q is a function. Similarly, the preimage of the empty set is always the empty set. And now we know that both X and the empty set are open sets in X because the topology on X satisfies this first condition. So we're good on this first point. The second condition is that we need the topology to be closed under arbitrary unions. For this, we suppose that we have some UIs, which are open subsets in the quotient topology. And now we need to show that their union is also going to be an open set. And again, we just apply the definition. We have that the inverse image of this union of the UIs, well, this by properties of preimages is going to be the union of the preimages of the individual UIs. We know that each of these preimages is open by how the open sets in the quotient topology are defined. And so now we have a union over open sets in the space X, which is again an open set because the topology on X is a topology and hence is closed under arbitrary unions. So the second point is also satisfied. And finally, we need the topology on Y to be closed under finite intersections. And well, the proof for this is very similar to the case for the unions. We just have to replace the union by a finite intersection. So here we write an intersection. And now we in addition assume also that these UIs, there are only finitely many of them. And now the same argument works because in order to find out whether this finite intersection is an open set, we consider its preimage. Preimages are again going to be compatible with the set operations, in particular the intersection. So we can pull the intersection out of this preimage. And now we have a finite intersection over some sets which we know to be open in the space X. And therefore, by the fact that X is a topological space, this finite intersection of open sets is again going to be an open set. So therefore, this preimage is open, meaning that the intersection here is open by definition. So this concludes our checking that the quotient topology is indeed a topology. And perhaps this proof also illustrates why I said that we can think of the quotient topology as being a way of pushing the topology X forward along the function Q. Because in this proof, in order to show that certain things were open, we always had to kind of pull them back again along Q in order to check certain properties. Then we showed those properties in X, and then we could push the result forward again along the map Q. All right, so we've defined this thing called the quotient topology, which as prerequisites just requires some topological space and a surjective function from that topological space to some set. So this construction is very general, but that also means that probably if you're seeing this for the first time, you have no idea what it's supposed to mean. That's why for the rest of this video, we'll just be looking at ways of thinking about the quotient topology and seeing very many examples of it. The first thing that's going to be very helpful towards this end is going to have different ways of looking at surjective functions. So let's think about the situation we were considering in the definition where we have two sets, x and y, and we have some surjective function q going from x to y. Now, because q is surjective, we know that every point, small y, in the set capital Y is going to be the image of some points in x. Now, in general, q is not going to be also injective, so we could have multiple points in x being mapped to this single point, small y, in y. So what I've drawn here in pink is going to be the preimage under the map Q of the singleton containing y. And we call this set the fiber over the point y. Now this small y was just one point in the set capital Y. There can also be other points, for example z. And here we can again consider the fiber over Z, so that's the pre-image of the singleton containing Z. And this will again be some subset of the set X. Now we can continue on in this fashion and consider the fibers over every point in Y. And these fibers will subdivide the set X. Observe that these fibers will be mutually disjoint, because if, for example, we have some point X in the fiber over Z, so that means that X is mapped by the function Q to the point Z, then X cannot also be in some other fiber, because if, for example, X were also an element of the fiber over Y, that would mean that X is mapped to Y by Q. But we know that Y and Z are distinct points, and a function can't map a single point in the domain to two distinct points in the codomain. Therefore, each point in X is in at most one of these fibers. Furthermore, each of these fibers is going to be non-empty because the function Q is surjective. In other words, for every point in Y, consider the fiber over Y, well, we know that because Q is surjective, there's going to be a point that maps to that point in Y we're considering, therefore that fiber is non-empty. In conclusion, thinking about these fibers over all the points in Y gives us what is called a partition of X. This just means that we are expressing X as a disjoint union of non-empty sets. So this is a disjoint union of non-empty sets, well, such that the union is equal to X. Hence, going in this direction, we can start with a surjective function and obtain a partition by considering the set of fibers over points in Y. Now, this partition picture is really useful because it allows us to sort of think about Y as being a collapsed down version of X. To see this, consider each of these fibers over the points in Y, and now think of this fiber, so this entire set, as being collapsed down to the single point, say Z in Y, by this function Q. So Q takes this partition and collapses each of these sets that make up the partition into a single point in Y. Now we can actually also perform this construction in reverse. Suppose that we have some partition of X that is indexed by Y. So this just means that we have some subsets of X that are disjoint and non-empty, and we have one subset for each point in Y, and moreover, the union of these subsets is X. Then we can define a surjective function going from X to Y by sending each point small x in X to the point in Y that corresponds to the partite set that this point small x is located in. So if X is equal to the disjoint union over some sets Sy for each point Y in Y, then the map Q sends a point X to the point Y where Y is the point such that X intersected Sy is non-empty. This works out because X is the disjoint union over these sets Sy, so the point small x lies in exactly one of these sets, so this assignment uniquely defines some point Y in Y. Moreover, because each of the Sy is non-empty, so that's part of the definition of a partition, it means that each of these Sy contains at least one point X that will be mapped to the corresponding point y in y, making this q defined in this way a surjective function. This maybe looks more complicated than it actually is. So if we have some x and we have this partition of x into, say, sets 1, 2, 3, 4, and we assume that these indices are precisely the points of some set y, 1, 2, 3, 4, so that's our set y, then this function that we're defining, q, simply maps each of these partite sets corresponding to the index to the corresponding point. So every point in the partite set corresponding to 1 gets mapped to 1, and every point in the partite set that is indexed by 2 gets mapped to 2, and so on. So you can now see that this picture is basically just the same picture we had before. In summary, if we have some surjective function q going from a set x to y, then this corresponds to a partition of x that is indexed by points in y by considering the fibers over each point in y. And conversely, given some partition of x indexed by y, we can construct a surjective function from x to y. Now, it's easy to see that these two processes are inverse to one another. So if you start with a surjective function, then construct a partition based on that function, and then construct a function based on that partition, the function you'll get back from that process is the same thing as the function you started with. And similarly, if you start with some y-indexed partition of x, then construct this surjective function as I've defined here, and then consider its fibers, that partition will be the same partition you started with. Therefore, we have a one-to-one correspondence between surjective functions from x to y and partitions of x that are indexed by the points of y. So basically, these two things are just two different ways of thinking about the same thing. The way I've described this correspondence here is pretty formal, but you can just look at this picture and switch between both views. So you could either think of this picture as describing some surjective function from x to y, or you could think of it as being a partition on x that is indexed by y. All right, next I'm going to give yet another way of thinking about the same thing. So we again consider some set x, and now we assume that we have some partition on x that is indexed by some set y. So I'll again call these partite sets 1, 2, 3, and 4. Now there is an obvious relation you could consider on the points of x. Namely, you could set x being equivalent to x prime if and only if x and x prime lie in the same partition. So for example, these 2 points here, x and x prime, they would be related to one another. However, if we have some point z over here, z would not be related to x or to x prime. And in fact, it turns out that this relation defined in this way is an equivalence relation. Just as a reminder, an equivalence relation is a relation such that each x is related to itself. Next, an equivalence relation is symmetric. So if x is related to y, then also y is related to x for all x and y. And finally, equivalence relations are transitive. So if x is related to y, and also y is related to some z, this implies that x is related to z for all x, y, and z. Okay, so with that reminder out of the way, we can check that this relation defined in this way is actually an equivalence relation. So first off, we need to check that each point is related to itself. Well, if you look at the definition, a point being related to itself simply means that x and itself, x, lie in the same partition, which is obviously true. So that holds. Next, symmetry also follows directly from the definition. Well, if x is related to y, then x and y lie in the same partition. But this also means that y and x lie in the same partition, so y is related to x in the other order as well. Finally, the transitive property also follows directly from the definition. So suppose that x and y lie in the same partite set. And we also suppose that y and z lie in the same partite set, so z would also have to be here. Well, then obviously x and z also lie in the same partite set, so x is related to z. Great, so we've shown that if we start with a partition of x, we can construct an equivalence relation on x. And moreover, if this original partition was indexed by some set y, then the equivalence classes that we get based on this equivalence relation will also be indexed by y. Now, just as a reminder, equivalence classes are just the sets of points that are all related to one another. So for example, the equivalence class of a point x, this is just all the points z such that z is related to x. Now, in fact, if you have an equivalence relation and you consider its equivalence classes, so that's all the classes of points that are related to one another, well, then this forms a partition of the original set x. Therefore, if we start with an equivalence relation, then we can go back to a partition by considering equivalence classes of this form. So let's see how this looks in a picture. So suppose we didn't have this partition, all we had was some points in x, and we knew that certain points were related to one another. And what I'm drawing here in these different colors are all the points that are related to one another. So any two of these purple points are related to one another, any two of the yellow points are related to one another, and so on. So we start with some equivalence relation. This tells us what points are related to what other points, and now we can just consider the equivalence classes. So we think of all the points that are related to some specific point. So for example, we could think of this point as being x, and now we think of all the points that are related to x, which will be all of these purple points. So these purple points here will form the equivalence class of this point x. And in a similar fashion, if this is, say, some point y here, this yellow point, then all the yellow points will form the equivalence class of the point y. Then we have another equivalence class here in orange. Finally, we have some equivalence class in green. And now by the properties of this equivalence relation, the resulting equivalence classes will be mutually disjoint and non-empty, and moreover, their union will be the entire set x. In other words, the equivalence classes will partition the set x. In more detail, because each point is related to itself, it means that each point will be in some equivalence class. This already shows that the union of the equivalence classes will be the original set, and that all of these equivalence classes will be non-empty. So the only thing we need to show is that the equivalence classes are disjoint, and this follows immediately from these two last properties, because suppose that y was simultaneously in the equivalence class of some x and some z, well then this by definition means that y would be related to x, and also y would be related to z. But now we know that y being related to x also implies that x is related to y. But now we have the situation where x is related to y and y is related to z. So this implies that x is related to z. And this shows that x is in the equivalence class of z and z is in the equivalence class of x, which means that these two original equivalence classes were actually equal. Therefore, if two equivalence classes share a point, then they coincide, which means that all equivalence classes that are distinct must be disjoint. All right, again summarizing, we've seen that if we have a partition of x that is indexed by y, then we can generate an equivalence relation on x whose equivalence classes are indexed by y. And conversely, given an equivalence relation on x whose equivalence classes are indexed by y, we can just consider the equivalence classes, so the set of equivalence classes, and these will partition the set x into a partition that's indexed by y. And again, these two processes are mutually inverse. So in fact, we have a one-to-one correspondence between partitions of x that are indexed by y and equivalence relations on x with equivalence classes indexed by y. Now composing this with the correspondence we saw before, We can also see that a surjective function is basically the same thing as an equivalence relation on X with equivalence classes that are indexed by the codomain Y. Now this correspondence will be super useful when we look at quotient spaces because it essentially gives us different ways of defining surjective functions which will then yield certain quotient spaces. So instead of just defining a surjective function, you could also start with some partition of some space X in order to get a surjective function from X to some set. Or alternatively, you could start with an equivalence relation on X, and via this correspondence, this will again give you some surjective function from the space X to some set. So let's see how we can exploit this correspondence in the following examples. For our first example, we'll consider the following situation. We'll consider the unit interval going from 0 to 1. That's a subset of the real line. And this will be our space X. This implicitly means that we're going to use the subspace topology on X that is induced by the usual topology on the real line. Now the idea is that we're going to want to identify these two endpoints, 0 and 1, in some quotient space. Perhaps the easiest way to do this is to define an equivalence relation on X, then use the correspondence we saw before to get a surjective function from X to some set Y, and then put the quotient topology on that set Y. Since we'll want to identify the points 0 and 1, we'll set them to be equivalent in this equivalence relation. Remember that in order to have an equivalence relation, we also need that every point in the set needs to be related to itself. So we'll additionally set X equivalent to X for all X in the interval 0, 1. Finally, there was also this symmetry condition, so we'll also need to have 1 being equivalent to 0. So this entire thing here will define some equivalence relation, which we usually abbreviate with the same symbol we use as an infix for saying that two things are equivalent. So I'll just write this tilde for this entire equivalence relation. Formally, this thing is actually a subset of X times X. Now, having to declare an equivalence relation in this way is kind of tedious because it includes a lot of redundant information that isn't really of interest. For example, we know that every point needs to be equivalent to itself by the definition of an equivalence relation, so having to write that out is kind of annoying. And also here we've had to include this extra equivalence because of symmetry, but really it's already included in this information here. So usually what we'll do is we'll declare an equivalence relation by specifying a relation and then saying that the equivalence relation is generated by that relation. So in our case, this would be the equivalence relation that is generated by the equivalence 0, 1. So this just means that we're looking at the relation where 0 is related to 1, and then we take the smallest equivalence relation that contains that relation. So one way to think about that is you take all equivalence relations that contain this relation and then intersect them. That will give you the smallest equivalence relation that contains this relation. But that isn't very useful in practice. The other way to think about it is you start with this relation and then you add all other things that are implied by the definition of equivalence relation. In our example, we started here and then we had to add this by symmetry, and then we had to add this because each of the elements needs to be related to itself in an equivalence relation. But after that, we're done because there are no other requirements that need to be satisfied. And to be more concise, we'll usually abbreviate the equivalence relation generated by some relation just by brackets with the generating relation inside. And if we have multiple ones, we just separate it by commas. All right, so we have this set X, the unit interval, and we've declared an equivalence relation on this set. And now we need to come up with a surjective function that corresponds, via this correspondence we saw previously, to this equivalence relation. If you trace out the correspondence, what you'll get is a function q going from x to the set of equivalence classes of this equivalence relation. And the set of equivalence classes is usually denoted x and then this quotient by the symbol for the equivalence relation. So this here is just defined as the set of equivalence classes of points in x under the equivalence relation tilde. If you trace back these correspondences we saw previously, you'll find that this function q should map each point small x in x to its equivalence class in the set of equivalence classes. And it's immediate from this definition that in this case, this function q will be surjective. Now, explicitly in our example, the set of equivalence classes under this equivalence relation which identifies 0 and 1 is as follows. So it's going to be a big set containing other sets, namely the equivalence classes. So the first set it contains is going to be the equivalence class of 0, which is equal to the equivalence class of 1, since 0 and 1 are equivalent. And this is just the set that contains the points 0 and 1. And in fact, this is the only interesting equivalence class in this set, because every other equivalence class, for example, the equivalence class of 0.5, is just going to contain a single point, because that's the way we've defined this equivalence relation. So we've only identified 2 points, namely 0 and 1, so all the other points are just going to be left alone. Okay, so the set of equivalence classes would continue in this way. For every point that isn't 0 or 1, we have an equivalence class that just contains that point. This means that if we think about this function pictorially, where we have points 0 and 1 here, then the set of equivalence classes is basically going to be the same set, except that we'll have some new point, which corresponds to the equivalence class of 0, which is the same thing as the equivalence class of 1. And all points except for 0 and 1 will be mapped 1 to 1 to their equivalence classes. However, 0 and 1 will both be mapped to this new point. All right, so that's how this map Q works as a function. And now we are in the situation where we have some topological space X, namely this unit interval considered as a subspace of the real line, and we have a surjective function Q going to some set, in this case the set of equivalence classes on X under this equivalence relation we've defined. This now enables us to put the quotient topology on this set here. And as a reminder, this is just the topology where we declare a subset to be open if and only if its pre-image under Q is open in the original space X. So let's think about what the open sets would be in this quotient space. So if you think about any set that is a subset of this portion where we haven't identified any points, if you look at its pre-image under Q, it'll look exactly the same in the original set X. Therefore, the open sets of this part of the quotient space that do not contain this point where we've identified stuff, those are just going to be the sets that correspond to unions of open intervals in the original space. So the interesting case is going to happen when we include this point that corresponds to both the points 0 and 1 in the original space. Now first let's think about the subset that just consists of this point. Its pre-image will be both the points 0 and 1, and these 2 points are not an open subset of the space X. Recall that a set is open in the subspace topology if it's the intersection of some open set of the larger space with the subset. Therefore, the open sets of this subspace X, so that's the closed interval from 0 to 1, are going to be precisely intersections of this closed interval with open sets of the real line. And you can't obtain these 2 single points by intersecting X with open sets of the real line. However, if we were to add a little half-open interval to each of these points, then the corresponding subset of X would be an open set. This is because if you have the real line here and you have the closed interval 0, 1 here, you can intersect it with open intervals like this, and this will give you half open intervals in the intersection as subsets of the closed interval 0, 1. And now if you look at what happens to this new set we've drawn, when we map it via Q to the quotient space, this will include still this point where we've identified 0 and 1, but also little half open intervals in the other portion of the quotient space. So these types of sets, as I've drawn on the right in the quotient space, those will also be open sets in the quotient topology. And in fact, they'll be the only type of subset that includes this point here that are open. Because as soon as we include this point, we have the situation where we have these two isolated points in the pre-image, and so we need to add little half-open intervals to them in order to make it an open set. So the only open sets including this point will also have to include these little bits here in the quotient space. Now if you do some lateral thinking, you'll see that a much better way to draw this quotient space is actually as a circle. And here we have this point where we've identified 0 and 1, so this is the equivalence class of 0 and the equivalence class of 1, and the rest of the space is just singleton equivalence classes which correspond to the points of the real line. And now our pictures for the open sets make a lot more sense, because if we have some sets that don't include this pink point, then these are open precisely if they correspond to open sets in our subspace X. So those would consist of unions of these open intervals. However, as soon as we include this pink point, we also have to include a bit around it to make it into what is now an open segment of this circle. So this strongly suggests that the space we obtained by identifying the endpoints of this closed interval will be homeomorphic to a circle. This is in fact the case, and it's something you could prove directly by explicitly constructing a homeomorphism and doing some case analysis on the open sets. However, the proof will be much easier once we have the tools we're going to introduce in the future videos on quotient spaces. To conclude this example, we started with this space X and we identified some points via an equivalence relation. Then we saw that this equivalence relation corresponds via the correspondence we looked at previously to such a surjective map Q, and we then use this to endow the set of equivalence classes with the quotient topology and saw that this then looks a lot like the circle with the usual topology. This might have seemed a bit complicated, but all of this is really just a way of making something really intuitive formally viable. So the intuitive idea is that if you have some piece of the real line and you think about identifying its endpoints, well, then what you would do if this was like a physical piece of string or something like that is you would bring the endpoints together until eventually you have a circle like this where the endpoints are identified. And in fact, this process is basically just described by this surjective function Q, and the quotient topology on this new space is just a natural way to put a topology on this space where we've identified certain things. So in practice, what you'll actually do is you'll start with an idea like this, where you think about having some line segment and wanting to sort of join the ends into a circle. And then the way to describe that properly in terms of the machinery we've built in topology is to use quotient spaces. This also means that for most of the quotient space constructions, it's actually sufficient to have this sort of intuitive idea of what's going on. And then if you need to check more specific things, then you need to be able to dig into the details to be able to like rigorously prove things. So in the next examples, I'll probably provide less details on how you would like explicitly do all of this with the equivalence relation and so on, and just present the intuitive idea behind what we're going to be identifying and what the resulting space will look like. For the next example, we'll be considering the closed disk, which we denote B bar 2, and this is a subset of the plane. So this is just all the points that have radius less than or equal to 1 from the origin. So this includes this boundary. Perhaps it's useful to have the coordinate axes here. So this is the x-axis and this is the y-axis. So what we're going to do now is we're going to identify the points on the boundary of this disk that lie on either side of the y-axis. And the way I'm going to draw this is with these arrows going in the same direction. So what I mean by this is if we have a point here, then we're going to identify it with a corresponding point on the other side of the boundary that's at the same height. Now formally, we're again going to express this as an equivalence relation. So the equivalence relation here is going to be generated by the following assignments. Namely, we're going to declare a point x, y to be equivalent to x, minus y. And again, with this notation, this means that it's the equivalence relation that's generated by this assignment. So we also have that each point is equivalent to itself, and we have that this thing is closed by symmetry and transitivity. Okay, so now let's think intuitively about what the quotient space of this thing will look like. So the idea we're going to use is we're going to think about this identification as being us gluing the points we're identifying together. So in the first step, we have this disk, and we haven't identified anything yet. What needs to be identified is this boundary, so you can think about us applying some glue to this boundary. And now what I'm going to do is I'm going to try to fold this disk along the y-axis. To draw this, it's probably easiest if we first rotate by 90 degrees so that the y-axis is somewhere here, and this is still the disk, and this is still the boundary. So you can think about this disk as being made of paper, and you're holding it in your hand, and now you're folding both sides upwards so that the crease lies along this white dotted line. And I'll try to draw this as best I can. So in an intermediate step, we'll have this bottom bit creased here, and we'll have the top bit like so. And the boundary is all of this stuff along here. So I hope you can imagine what's going on here. Another way to think about this is that if you know what a tortilla is, you can think of this thing as being a tortilla, and now you're folding it in half like a taco. And now remember, we've applied glue to the red portion, so we're going to glue these bits together. So you can imagine folding it more so that these red portions all overlap with each other and become glued together. And the result of this will be like this half disk where both the boundaries have now been identified together, but this interior part in blue has not been glued and is still hollow. So in this picture, this white crease would be at the bottom. And maybe it's again good to draw this a bit rotated. Like so. So the point is that this boundary here on the outside has been glued together, but there's really still two layers here in blue that have not been glued together. Now, because this result here on the right-hand side is hollow, except for where we've glued together, but that's just one line, we can think about inflating it. And eventually what will happen is that this thing will actually look like a sphere. So on one side of the sphere, we have this portion in red, which we've identified, and on the back side will be this white crease line that I've drawn. And we've just inflated out these blue bits on the side here. So going by our intuition, where we thought about this process of identification as like a physical manipulation of the space, this leads us to believe that this disk quotiented by this equivalence relation we've defined below should be homeomorphic to the sphere S2. And this is in fact the case, and it's again something that we'll be able to prove once we've developed the tools that we'll introduce in the future videos on quotient spaces. For our next example, we'll start with a square, which we can think of as the closed unit interval I. So for abbreviation, let's denote the closed unit interval by I. So this square will be the product of I with itself. And now what we're going to do is we're going to again identify portions of the boundary of this space. So we're going to identify these two portions of the boundary together in the direction that I've indicated. And we're separately going to identify these two sides of the square, again in the direction that I indicate. Formally, we again have to specify some equivalence relation that expresses this identification. And for this, we can coordinatize the space I cross I as follows. We have 0, 0 here on the left bottom point. Then we have 0, 1 up here. This would be 1, 1, and this would be 1, 0. So we just think of this space as being embedded in R2. Okay, and so this allows us to define an equivalence relation as follows. So we generate, again, an equivalence relation by a relation. And what points are related? Well, we want the points on the top and the bottom in yellow to be related with one another. So notice that any point on the top yellow arrow here will have y coordinate 1. And notice that on the bottom, it'll have the same x coordinate, but y coordinate 0. So for the yellow part, this means that we'll want any point x1 to be equivalent to any point x0. And for the red identifications, we'll do something similar. We notice that on the red line, we have x coordinate 0 or 1 respectively. So we'll want that 1y is identified with 0y. So the quotient space we're considering is this I cross I quotiented out by this equivalence relation with the corresponding quotient topology on it. Okay, so what does this space look like? Well, we'll again do some intuitive derivation of what we would expect the result to be. So here I have these red identifications going on and these yellow ones. And now what we're going to do is we're going to think about this blue square as a sheet of paper. And first, I'm going to try to bring the yellow portions of the paper together. So what this will end up doing is it's going to create a cylinder. And at the cylinder, let's say we've put the yellow portions both at the bottom of the cylinder. And now we still have some identifying to do, namely these red portions. Those boundaries will be the parts that I've drawn in red, and the arrows will be pointing in the same direction. So this transformation is something you can easily try out with a piece of paper at home. You just form the piece of paper into a cylinder. Now the next part we're going to do is something that's harder to do with a piece of paper, namely we're going to bring these red boundaries together. We can draw an intermediate stage of this transformation, which might look something like this. So here, this yellow identification that we've already made would be down here. And these red boundaries are here, and we now only need to keep track of the direction in which the arrows are going. So these arrows have to go in that direction, and these other arrows will be pointing down in this direction. And now the goal is to make these two red circles overlap. And if you think about bringing them together, what you'll end up with is a hollow donut shape. So here, the red identifications will have happened here, and the yellow identification will be going along all the way around like so. And the red identifications will be pointing upwards in this case. Okay, and so the space we're considering is just the surface of this donut shape. So this is a torus, which we denote T2. Therefore, by our intuitive derivation, we would expect this quotient space here to be homeomorphic to the torus. Again, this is something we'll be able to actually prove fairly easily once we have the tools we'll establish in later videos. Next, we'll look at a fairly general construction we can do, which involves collapsing a certain portion of a space down to a single point. So here I can just consider some arbitrary space X and some subset A of that space. And now I'm going to declare an equivalence relation on this space as follows. I'm going to say that A is equivalent to A prime for all points A and A prime in the set A. So what's going to result in the quotient is that we'll have basically the same space X, except that all the points in the set A will now be collapsed to a single point. So this is actually X quotiented by this equivalence relation. So just to give some intuition on this construction, if you think about, say, the sphere, and you think about some subset A, which is like a patch on the sphere, then if you quotient out by this patch, basically you're just shrinking a part of the surface of the sphere down to a point, and this result is still going to be homeomorphic to the sphere. So here we have a case where we started with a space S2, and we quotiented S2 out by some equivalence relation which identifies all the points in A, and the result is actually again going to be homeomorphic to the original space S2. Of course, this doesn't always work depending on how you choose your set A. For example, if we choose some portion of A at the top of the sphere and also have some portion of A which is at the bottom of the sphere, then if we identify what's going to happen is actually that, well, all of this is going to be collapsed to a single point, but this means that we actually have like one point at the top of the sphere and one point at the bottom of the sphere that are like the same point. So this line I've drawn here isn't actually like a piece of a line. It's meant to mean that these points are actually still going to be identified. So if you think about what this would look like, well, you take a sphere and you identify the north and the south pole together. So you can think about this as being like an inflated beach ball or something like that. And now you press in on the top and the bottom of the beach ball until the 2 points meet. So what you'll get is fairly hard to draw. So it's kind of going to still be like a sphere, but you have this indent on the top and also at the bottom. So this portion here on the inside is going to be hollow except for where this middle point is. So I hope you can do this better in your imagination or like with an actual physical object than my drawing. But this is just to show that depending on what subset of the original space you choose, the result might be different if you identify all the points in that set. As our final examples, we'll look at two more constructions which crop up fairly frequently. And the first one is called the cone on a space X. So for this, you start with some space X, like so, and then you take its product with the closed interval 0, 1, which we've abbreviated I. So in pictures, this just means that we're extending this space, like so, along the interval I. So in this product space, we have a copy of the original space X for each point in the interval. So in particular, we have one for 0 and one for 1. And then we have all the other points in between. So this is like a filled out cylinder that has as a base surface the space X. We now quotient out this space by the following equivalence relation. Namely, we say that the points X and Y are equivalent if they are contained both in the copy of X that is at the 0th level of this product. So that's taking this set here, which I've drawn in orange. This is the set X cross the singleton 0. And we're identifying all points in the set. If you think back to the previous example, this is precisely that situation where we set A to be the set X cross the singleton 0. Now, if you think about what happens if we go to the quotient space, all of this X cross 0 will collapse to a point, but the rest of the space will remain the same. So the result will kind of look like a cone, where at the top of the cone, we still have some copy of X. And actually at each level of the cone, we still have a copy of X, except for at the bottom level where we just have a point. So this thing here, this quotient space, X cross I, quotiented out by the equivalence relation that I've defined below, this is called the cone on X and denoted Cx. I guess I forgot to mention in the previous example that if we quotient out by some equivalence relation that stems from identifying all points in a set, we also sometimes write, instead of this quotiented by the equivalence relation symbol, we can also write this as the set quotiented by the set we're identifying. So in this case, this would be X cross I quotiented out X cross the singleton 0. So in the previous example, this set here would have been called A, and our notation would just be the original set quotiented out by the set A. That just means that we're identifying all the points in the set A. Okay, and now for our final example, we'll consider what's called the wedge sum. So for this, we take some spaces x1, x2, and so on, up to xn. And now for each space x, we declare some base point. So this would be small x1, small x2, and small x3. And now their wedge sum is defined to be the quotient of the disjoint union of these spaces by the equivalence relation that identifies these base points. So what we have to do is we first have to consider the disjoint union space that consists of all of these xi. And on this disjoint union, we declare an equivalence relation where we say that xi is equivalent to xj for all ij where this makes sense. And now we consider the quotient space where we quotient out the disjoint union by this equivalence relation, and this will be called the wedge sum over the xi's. And so this wedge symbol here, this is like a V, and you can also write it for like finitely many, so this would be the same as writing x1 wedge, x2 wedge, and so on up to wedge xn. Okay, and the picture for this is just that we have these spaces, x1 and so on, and there's a single point where all of these base points of these spaces have been identified. So here we have the space x1 with the base point small x1, and then attached to this is also the space x2 with base point small x2, so x1 and x2 are now identified in this wedge sum, and so on until we have a space xn with base point small xn, which is also identified in this red point. So the wedge sum is just a way of gluing multiple spaces together at one single point, and in order to do this, you just have to specify what point you're going to glue for each space. Okay, this concludes what I wanted to say in this first video about quotient spaces. I hope that these examples have given you some intuition for how this very general construction of quotient topology can be used to perform a lot of very intuitive operations. Perhaps as an exercise, you could take some physical object and think about gluing certain portions of it together, and then think about how you would write that down formally in terms of a quotient space of that original object. You'll also notice that in many of these examples, I said that we would intuitively assume that certain quotients are going to be homeomorphic to spaces we already know, but I always said that we would prove that later once we have better tools to do so. Therefore, I hope that this video will strongly motivate you to learn the tools that we'll be examining in the future videos on quotient spaces that will make it fairly simple to argue that these intuitive ideas we get from our physical intuition actually translate into the theory. So we'll in particular be able to prove, for example, that if we have an interval and identify the endpoints, that this space is actually going to be homeomorphic to a circle. In fact, many of these types of arguments will involve the universal property for the quotient space, and this actually provides a very nice illustration of how these very abstract universal properties can interact nicely with something very intuitive, namely our physical intuition of how quotient spaces should behave.